Good morning. This is the video for section 1.3 continued. We started it in class Thursday, and we'll finish it up by looking at these examples on the video. I'm starting out on page 62 in your book. And if you remember where we were Thursday, everything that we tried to take the limit of, we were able to just do direct substitution. We just took whatever number x was approaching, and we just plugged it in, and that gave us the value of the limit. And that was because all of those function types were well behaved. They were continuous at that point. They were polynomial functions, they were rational functions, they were square root functions, and they were all well behaved at that point. Well, today we're going to find a strategy for dealing with functions that are not well behaved at that point. They're not continuous for whatever reason at that point. So I'm going to pick up with example 6. Find the limit as x approaches 1 of x cubed minus 1 over x minus 1. So as we try, because our strategy is always, let's just try direct substitution, because if it works, it's great. So we try to plug in 1, and we get 1 cubed minus 1 on the top, which is 1 minus 1, which is 0 on the top. And on the bottom, we get 1 minus 1, which is 0. And 0 over 0 is not 0. You can't take nothing and divide it up into no number of pieces. So it's something called an indeterminate form. The prefix in means not, so we can't determine the answer. So when we get an indeterminate form, and we don't even have to go that far, I wouldn't even check that way, honestly. All I would check would be the denominator. If you plug 1 in and you get a 0 down there, you can't divide by 0, so automatically direct substitution won't work. So we need a different way to go. So one of the things that we'll try to do is we will try to factor and use the dividing out technique. And when you look at the numerator, you might remember that it could factor, and then again you might not, because this form may not have occurred very often in pre-calculus, but it might have, and you might have been introduced to it in Algebra 2. This form right here is a difference of cubes. So forgive me if you do remember it. We're not together, so I can't ask you. So a difference of cubes is a cubed minus b cubed. And the way you factor something that is a difference of cubes is it's a minus b times a squared plus ab plus b squared. People call this the SOAP method, SOAP, and we're just looking at the signs right here. This sign is the same as what we started with. This sign is always the opposite of what we started with, and this is always positive. So we can remember SOAP and help us to get our signs right. Same is true for the sum of cubes. It's always same, opposite, always positive. So there's your sum or difference of cubes. If you want to do the shortcut of putting two formulas in one, then you can do the difference formula in the top. All the signs for it are in the top, and all the signs for the sum formula we could put on the bottom. And since it's plus both times, we would just do a plus. Okay, so I'm going to erase all of this and get back to the problem that we were looking at. First, I think I'll erase this part. So this is a difference of cubes. A is x. The cube root of x to the third is x. And b is 1, because the cube root of 1 is 1. So then we would just say this equals the limit as x approaches 1 of a minus b, so x minus 1, times a squared, same opposite, ab, so 1 times x, plus, always positive, b squared. 1 times 1 is 1. And we still have our denominator. And remember, I just erased the part that said we were using the factoring and dividing out technique. So we should have a term, not a term, a factor in the top that can divide out with a factor in the bottom. And since these are both factors here and they're getting multiplied, they can divide out because x minus 1 over x minus 1 is 1. So now this simplifies to the limit as x approaches 1 of x squared plus x plus 1 in parentheses. And now you can do direct substitution. You can plug in that 1. 1 squared is 1 plus 1 plus 1 is 3. And here's the reason why this works. If you look above this example in the book, I'll show you also. Uh-oh, that didn't work. So I'm a little shaky. There we go. So here, if we look at this theorem, let C be a real number, and let f of x equal g of x for all x not equal to c. So in the problem that we're looking at, the c is 1, and the f of x, sorry, I dropped my iPad. The f of x is my original function. The g of x is my new function that I got after I divided out the common factor. These two functions are equal to each other. In fact, if you plugged in their graphs, one of them in y1 and one function in y2, the graphs would look identical. The only thing would be different would be if you looked at the table for this function right here, it would have an error at 1. And if you looked at the table for the simplified function, it would not. So let's go back to that theorem. These two functions are equal to each other for all x except for 1 in the open interval that contains that number 1. If the limit of g of x as x approaches c exists, then the limit of f of x as x approaches c exists. So back here, if this limit exists, which it did, then it's equal to the limit of the original thing. That's all that theorem is saying, but that's very handy. That's what allows our dividing out technique to work. Alrighty, example 7. And if any of these don't make sense or you want to talk about them again on Wednesday, please just remember to ask me about it because I'm happy to go over them once we're together again. You could also email me. We could try to talk about it through email. Okay, so our strategy is always, can I just do direct substitution? So we try to plug in a -3 right here, and we get a 0 on the bottom. So no, direct substitution doesn't work. So far we have one strategy that we can try, and it's the dividing out technique. So it was factor and see if anything divides out. Well, the top is a quadratic that does factor into two linear factors, x and 3 and 2. I need the 3 to be positive and the 2 to be negative. And this term sitting down here in the bottom, that's a pretty good hint for what one of your factors is going to be. You still want to check it by foiling and being sure it works, but it's a pretty good hint. So through the dividing out technique, that's gone. So it equals the limit as x approaches -3 of the simplified version of it, just x minus 2. Now we should be able to do direct substitution. Negative 3 minus 2 is negative 5. So it's super handy. It's really a really great technique. Then we turn the page to page 64 and we learn about another technique called the rationalizing technique. So if I can't factor it, maybe I can rationalize it. I just want to remind you of a couple things. A conjugate is a vocabulary word you've probably heard before. If you have the factor a plus b, its conjugate is a minus b. The only thing that changes if these signs become the opposite. So if you have 4 minus x, let's even make it be negative 4 minus x. The only thing that changes is the sign in the middle becomes the opposite. And so we'll be multiplying by conjugates to rationalize. Example 8. Let's find the limit as x approaches 0 of the square root of x plus 1 minus 1 all over x. So on the test, these limit problems are all going to be mixed up. Some of them are going to be direct substitution. Some of them you might have to factor and divide out. And some of them you might need to use this new technique. So you don't know what type it's going to be when you look at it. And you're always going to try direct substitution. And it's smart to just always try to plug that value into your denominator. See if you get division by 0. And we do. So direct substitution doesn't work. This will not factor. So we're going to have to try a new technique. We're going to try the rationalizing technique. And when we do that, we multiply by the conjugate of the numerator or the denominator. Not both, one of the other. Okay, so pause it if you need to write that down. I'm going to go ahead and erase that so I can do the multiplication right there beside my problem. So my numerator will have a conjugate because it has one term and a second term. So the conjugate is just the first term with the opposite symbol here and the second term. Now, it's not legal to just multiply by some random value. You can't change the problem. So to take care of that, we multiply the denominator also by that value. And something over itself is just equal to 1. So that's why we're allowed to do that. Then what we get, let me review you on conjugates a little. So if I have x minus 2, my conjugate is x plus 2. When I FOIL this, I get x squared. My outer is 2x. Inner is negative 2x. My last is negative 4. And every time you multiply a number by its conjugate, the outer and the inner cancel. So we don't do FOIL when we multiply conjugates. We just do the first term times the first term minus last times the last. So we do a squared minus b squared. Okay, let me delete that. So we're going to multiply these conjugates together. So we just need to do that times that. Well, the square root of x times the square root of x plus 1 is the same thing as the square root of x plus 1 squared. Minus b times b, or 1 times 1 is 1. And in the denominator, I would not distribute. I would do x, and then I would do times parenthesis all that. Because remember, something nice is probably going to happen. Okie dokie, let's rewrite our limit. We have to keep writing limit as x approaches 0 each time until we actually take the limit, which means until we actually plug the 0 in. So when you square a square root, those are inverses of each other, and you have freed what was underneath. So that's what our new numerator is. We are still not going to FOIL out, or I'm sorry, distribute the denominator. Now, plus 1 minus 1, those are gone. They cancel each other. So the numerator is left with just an x in the top. And the denominator has x times x plus 1 plus 1. And you see right here, now we can sort of do the dividing out technique. I have an x in the top and an x in the bottom. That's a 1. So that's equal to the limit as x approaches 0, leaving just a 1 in the numerator. I can drop those parentheses now. Once that has happened, you should be able to direct substitute. So when you plug a 0 right here, you get the square root of 1, which is 1. I'll just write it. Plus a 1. And then square root of 1 is 1, and 1 plus 1 is 2. So this complicated looking limit problem is actually equal to a half. Something I was just thinking I needed to tell you. Oh, so right here when I decided, I can now do my direct substitution. When I do the direct substitution and I write down what I get from doing direct substitution, I have dropped limit because we've taken the limit when we plugged it in. Okay. We've already talked about the squeeze theorem a little bit, or the sandwich theorem just a little bit. So we're going to go on to page 66 and look at example 9. The limit as x approaches 0 of the tangent of x over x. I can't remember if this showed up in our discussion on Thursday or not, but you might remember that the tangent of x is equal to sine of x over cosine of x. If you don't remember it, it is on the inside cover of our book. It's a quotient identity. I feel like it came up the other day. So let me just tell you this, where we're going to try to go. When class ended, we wrote down these two special rules. If you have the limit as x approaches 0 of sine of x over x, you don't have to do any work. It just automatically equals 1. And if you have the limit as x approaches 0 of 1 minus cosine x over x, you don't have to do any work. It equals 0. So I might be able to rewrite this and maybe take advantage of this fact. So let's see. We know that tangent is equal to sine over cosine. So we're going to rewrite it. And that is still all divided by x. Well, I'm not sure how you learned to handle problems like this before. That's like a fraction in a fraction. Or it's sine x over cosine x, all divided by x. Or it's this. Those are two different ways to write the same thing. So this is more like one of the division of fraction problems that you've done forever. When you divide fractions, you keep, change, flip. So we keep the first fraction the same. We change division to multiplication, and we flip the second term. We multiply by its reciprocal. So I don't go to the side and do this normally. I do think about making this a fraction, and I do think about working up here and changing it to multiplying by the reciprocal. So I'm no longer dividing, I'm multiplying by the reciprocal. Alrighty. So now I have equals the limit as x approaches 0 of sine x times 1 is sine x, and cosine x times x is x cosine x. You can't multiply with that x that's in the cosine function. That x is part of that cosine function. It's the angle, so it's trapped in there. Now look what we have. Ah, that's kind of interesting. So this may not seem legal to you, but it is. I'm going to rewrite this limit problem, and I notice I have a product down here. So I'm going to rewrite it as the product of the limits. So one of the limits is going to become sine x over x. The other limit is going to have the cosine x in the bottom. But what can I put in the numerator? Well, if I've already used the sine x, there is a little multiplied by 1 there that I could use. So I can do that. This is our rule. By definition, that's equal to 1. And this, I should be able to do direct substitution. So I can drop the limit and do 1 over cosine of 0. You can use your unit circle, you can use your calculator, but whatever way you decide to work this out, cosine of 0 is 1, and 1 times 1 is 1. Last example. I know this has been a little lengthy. Example 10. The limit as x approaches 0 of sine of 4x over x. Just in case I forget to say this at the end of the video, when you're doing your homework, some of them may work really nicely for you. Some of them might be very frustrating. You might feel like you've hit a type of problem that you just don't know how to tackle. It's impossible, even with the hour and a half that we have on some days, it is impossible for me to go over an example like every type of problem you would see. So we'll just try them. We'll try strategies that we think might work and see if they work. And if they don't, you put a star beside it and you can come in and ask me about it. I don't mind spending the first several minutes of class going over the homework to be sure we all feel good about it. Okay, this is super close to that same rule that we just used. And this might seem illegal, but I'll try to explain why it's legal. What I want is the sine of something divided by that same something. Well, here I have the sine of 4x. I cannot change that. That's the angle. But I can do something to get a 4x down here in the denominator. And what I can do is I can multiply by a fraction that has a 4 down there. That's going to give me a 4x in the denominator. But I can't just multiply by that. I've got to multiply by a 1. So I've got to multiply by 4 over 4. So when I do that, I might see that this 4, well, let me show it this way, equals the limit as x approaches 0 of 4 times the sine of 4x all over 4x. I might see this as a scalar and just take it out in front of the limit. And then this is that rule. It's the sine of something divided by the same something. And when that happens, it is just equal to 0. So this is 4 times 0, which is 0. Oh, wait a minute. I'm sorry. That's not the one that equals 0. That is the one that equals 1. So it might bother you that we can extend and change that formula to be 4x. Well, remember, x is just a variable. And who's to say that I can't come up with a variable that I'm going to let equal 4x? So then I could have rewritten that as sine of u over u. So it does fit this form over here beautifully. Alrighty, that's it for today. You do have some problems to try. Try to take your time on them. And if you get frustrated with one, you can star it for me. Okay, I'll see you all Wednesday.